Yeah, all right. So what we spoke about yesterday, I suppose I haven't written up, but what we spoke about yesterday was subspaces, and we're going to start today's lecture just by doing one more example on subspaces. And then today we're going to talk about Gauss reduction. This is basically just a review of things that we should know from MAM2084S. And Gauss reduction is going to be very important in this course. And then when we come back tomorrow, we'll start talking about generating sets. So the example I want to look at here of a subspace is slightly different from what we've done with the other examples, because now we're working in a vector space of functions. The examples we did previously, we were looking at, sorts of planes and lines and this sort of thing. And those were vector spaces. We were really working in Rn or Rm or Rk or whatever it was. We were working in some sort of vector space that we've got a very good intuitive or geometric picture of. And over here, we don't really have some sort of geometric picture of what a space of functions looks like. But still, we can go ahead and we can try to show that this over here, the set of all the solutions, must be a subspace. So for the set of all solutions to be a subspace, what we want is that those solutions, if you add any two solutions together, it should still be a solution, right? We should have a space which is closed under vector addition, and the vectors here are the functions which solve this differential equation. And it should be closed under scalar multiplication. So if we multiply a solution by some scalar, then it should still be a solution. And for the previous examples, I think we checked the vector addition and the scalar multiplication separately. You can check them at the same time just by checking arbitrary linear combinations, which is what we're going to do here. It's just an alternative way of checking that something is a subspace. So we should check let me just call this equation star. We should check that if y1 and y2 satisfy star, so does y3, and y3 will just be an arbitrary linear combination of these two, right? So this arbitrary linear combination is really checking scalar multiplication and vector addition at the same time. You can think of it as checking vector addition, because if alpha and beta were just 1, we have vector addition, and if beta is equal to 0, we have scalar multiplication. Right? So we were checking here scalar multiplication and vector addition at the same time. So right. You can check them at the same time instead of doing it separately. So we want to show that y3, this linear combination, is a solution to the differential equation. So we want to show that y3 satisfies that equation star. So maybe the best thing to do is to take y3 and calculate the derivative of y3. Right? So if we take the derivative of y3, that's just the derivative of this linear combination, alpha y1 plus beta y2. And one thing which is really nice about the derivative, I mean, we've never really thought about it in this way, but the derivative is a linear transformation acting on a function space, right? And so linear transformation in the sense that if you've got the derivative of a sum of two functions, the derivative of f plus g, that's the same thing as the derivative of f plus the derivative of g, right? We know this from first year, and the same thing, you can pull out a constant. So we could rewrite this by using the linearity of the derivative as alpha dy1 by dx, right? Alpha times by this first derivative, plus beta times by this derivative over here, right? And again, as with almost everything we do, all we do is exploit the linearity of whatever transformation we're looking at, right? So the derivative is linear. Now, the functions y1 and y2 are not arbitrary functions. The functions y1 and y2, we said, were functions which solved that differential equation star. So if we think about what that means, it just means that the derivative of y1 must be equal to xy1, and the derivative of y2 must be equal to xy2. So this next line, we could write this as alpha. This must be xy1 plus beta xy2. And that's just because y1 and y2 are solutions to this differential equation. And we can maybe take out x as a common factor here. So you get x multiplied by alpha y1 plus beta y2. And alpha y1 plus beta y2 is y3. So that's xy3. Right? So we have the derivative of y3 with respect to x is just xy3. And that is exactly the differential equation. So y3 is a solution, so an arbitrary linear combination of solutions to the differential equation is still a solution. So the solutions must form a subspace. Are there any questions about this example over here? Does everyone understand what we've done and how things work? From here to here. Okay, so the question is, how do we move from this line here up to that line there? Let's just maybe put this in over here. The functions y1 and y2 are not arbitrary functions. y1 and y2 are solutions to this differential equation that we wrote down earlier, right? So that differential equation, okay, let's just zoom out and we can fit it all on one page here. They solve that differential equation star, which means that if you take the derivative of y1, it should be xy1. So if you take the derivative of y1, it should just be xy1. If you take the derivative of y2, it should just be xy2. So it's because there are solutions. Okay.
How do you come about the y3 is equal to lambda?
They're right at the top. Okay, so we can choose y3 to be this linear combination because we know that what we want to check is we want to check that this set of solutions is closed under vector addition and scalar multiplication. So we've just taken that alpha y1 plus beta y2, that just looks like some sort of vector addition and scalar multiplication, but we're doing it all at the same time. If you wanted to do it separately, you could first start with, let's take y3 is equal to y1 plus y2, and check that that still works, and then you would take y4 is equal to alpha y1 and check that that works, and then you'd be done. All right.
So what happens if the differential equation had no solutions to begin with?
What happens if okay, so that's a good question. This particular differential equation, and we'll speak about this later on in the course when we get to differential equations, but this differential equation over here has a solution because it's a homogeneous differential equation, in the same way that we have homogeneous systems of linear equations. And like a homogeneous system of linear equations always has a solution which is the zero vector, a homogeneous differential equation always has a solution which is the zero function. So this, for example, would just be solved by the zero function, y is equal to 0 everywhere. But we'll talk about this in more detail when we get to differential equations later on in the course. But basically everything that we are learning now about systems of linear equations will apply to the differential equations.
But if the equation didn't have solutions, it wouldn't work, right?
If the equation didn't have, there's no way, let's see, so the only way this would fail to have solutions would be if it was non-homogeneous. And we know that if you add two solutions to a non-homogeneous equation, they're not going to be a solution again. Right? So as soon as it doesn't have any solutions because it's not homogeneous, it wouldn't have a subspace anyway because it's not homogeneous. So the failure happens at 2 points immediately as soon as you say, aren't there, and what happens if there are no solutions? So that's not a case that's going to come up, or it's not a case that we're interested in this course. All right. Okay, so let's keep going. We have to talk about Gauss reduction, which is very important but can be quite time-consuming to explain. And you're going to have to watch me carefully, since invariably I'm going to make a mistake with signs or subtraction or something at some stage. But we're going to try to solve the following problem. We're going to say let A be equal to this matrix, and it's a really big, ugly matrix. So it's 1, 4, 1, 2, 1, 1, 3, 1, 1, 1, 3, 6, 3, 4, 5. And we're going to have a vector B, which is the vector 4, 1, 2. We've got this matrix A, we've got this vector B. Yes?
You said the x times alpha is y1 plus b y2.
Yeah.
Because it's a linear combination of solutions, it's a subspace.
Yeah.
That if you prove that two solutions are linear combinations.
Yeah, if you prove that a linear combination of two solutions is still a solution, you've proved vector addition, you proved that it's closed under vector addition, and you proved that it's closed under scalar multiplication. So showing that an arbitrary linear combination, showing that you're closed under linear combinations is the same as showing that you're closed under scalar multiplication and vector addition. All right. So we're going to write down these two over here, A and B, and we're now going to try to solve. Let this be that and let this be this. Solve AX equal to B. And we can just stop and think about this for a moment. We know that that vector X, if we just think about the dimensions here, we know that X must be, how big must X be? I mean, how many components does it have? 5. It must have 5 components. X1, X2, X3, X4, X5. It has to have 5 components, otherwise this matrix multiplication isn't going to be well defined, right? Okay. So we know that X must be something like this. X1, X2, X3, X4, X5. So how do we solve this problem? Step 1, you write down an augmented matrix. Okay, and let's say we can do these step 1. So create an augmented matrix. Create an augmented matrix. Create an augmented matrix, and the augmented matrix will always be A, B, like that. That's basically the shape that we want to write down. So in this case, I'm going to write down, okay, I do have it here. 1, 4, 1, 2, 1, 4, 1, 3. Should actually draw this slightly smaller, since I'm going to want at some stage to fit 2 of these next to each other on the same sort of row. So I'm going to just actually grab it and yeah, I'm going to write it down like that. So that's just about the right size that we can fit a second copy of it off to the side, which is what we'll do later. Okay, so step 1, you write down an augmented matrix, and on the left-hand side of the augmented matrix, you have the entries of your matrix A, and on the right-hand side, you have your vector B. So if you are solving a homogeneous system, then the right-hand side, that's all just 0, which is very nice to work with. Otherwise, it's whatever vector it is that you're dealing with. In fact, let me now also just say one other thing. This entry over here is called the pivot entry, right? And the pivot entry is got to be in the leftmost, it's got to be as far left as possible, and it's got to be non-zero. And we want a pivot in the top row. So in this particular case, there are actually sort of 3 possible pivots. We could, for example, swap the third row and the first row and get that third row into the top row, and then use 3 as the pivot, maybe rescaling it by a factor of 1/3. But we'll see later on that we're not necessarily going to have pivots in every single column by the time we get to the end of the Gauss reduction. Okay. Yes?
Can you please explain what you just meant by using different pivots?
Okay, let me write down this, which is step 2 about choosing pivots. Okay. So choose a pivot element. So when you're choosing a pivot element, you look for the leftmost non-zero entry. In this case, we've got 3 leftmost non-zero entries. You move one of them into the top row. In this case, we don't have to move anything into the top row because it's already in the top row. And then you scale so that it's equal to 1. And I'll do an example now, just quickly, where we see where we have to do this. So choose a pivot element. And we do this by move one of the leftmost non-zero, move one of the leftmost non-zero elements Yes?
You make it sound like you're swapping values in the row without...
No, you swap the whole row. Yeah, I'll do an example now, right? So here's an example, and this is a, let's see, we'd have something like this. So say we've got a 0, 1, 1, 2, 3, 6, 0, 3, minus 2, 4, 4, 1. Right? So what we would do is we'd look at this, we choose one of the leftmost elements. You either choose that 3 or the negative 2. You can't choose the 0. Obviously, you've got to choose one of the leftmost non-zero elements. And we now first swap. So in this case, we would be exchanging, let's say we would exchange row 1 and row 2. So we swap all of row 1 with all of row 2. So row 2 goes up here. So this would be 3, 6, 0, 3. Row 1 drops down. That's 0, 1, 1, 2. And then the last row here is unchanged. And then we would scale so that that entry isn't a 3, it's a 1. So we'll scale it by a factor of 1/3. So we'd say row 1 is now going to be 1/3 of row 1. So 3 divided by 3 is 1, 2, 0, 1, 0, 1, 1, 2, minus 2, 4, 4, 1. And this over here is now going to be our pivot. Yes? It makes the next step a little bit easier if the pivot has been scaled to 1. And it also makes reading off the answer at the end also slightly easier if the pivot's been scaled to 1. I guess you could do Gauss reduction without scaling the pivot to 1, but then your calculations are a little bit messier. All right. Okay. Are there any questions about this step 2 over here? Right. For this particular problem, this bigger matrix that we're looking at, we didn't need to do any of that because we already had a value of 1 in the uppermost, leftmost entry for this augmented matrix. So we didn't need to bother with swapping rows or rescaling. Yes?
What about the values like in the x vector that had also, and they also don't swap because like the row which was multiplied, for example, by the x which is this now.
Oh, okay, so you're worried about, okay, so the x values correspond to columns, right? And we're operating here on rows. So those operations on rows, you could imagine, for example, if we wrote down just that line over there, that would be, say, 3x plus 6y plus 0z is equal to 3, right? That's what that line says. And now if you write down this one, that just says x plus 2y plus 0z is equal to 1, right? And the difference between these two equations is just you've divided one of these equations by 3. But dividing that equation by 3 doesn't change the values that work for x, y, and z. If there were values of x, y, and z that solve this equation, they're still going to solve this equation over here, right? So these row operations have no effect really on the variables that we have here in the columns. What would happen, what would have an effect, and I guess we could do it, but we don't ever really do it, would be if we were to exchange columns, because then we'd be relabeling we'd be exchanging the roles of x and y, for example. But we don't do that. We stick only with row operations. All right. Okay, so let's keep going. So we have this pivot, and then step 3 is to subtract multiples of the pivot row from all the rows underneath it to make the entries underneath the pivot equal to 0. Right. So this will be step 3. And I guess we can say add or subtract multiples of the pivot row subtract multiples of the pivot row to the rows beneath it, and we're doing this not just random multiples of the pivot row, we're choosing multiples that will make the entries underneath the pivots equal to 0. Add subtract multiples of the pivot row to the rows beneath it to make the entries underneath the pivot equal to 0. Okay. I'm going to copy paste this. Let's put it over here, right? So that over there was our pivot. So what we're going to do now is we're going to add or subtract multiples of row 1 from row 2 and row 3 in such a way that these entries over here become 0. And so we're going to take row 2, and row 2 will have to subtract one copy of row 1. So row 2 will be row 2 minus row 1, and we'll take row 3 and we'll subtract 3 copies of row 1. So row 3 minus 3 copies of row 1. So, I mean, this is what I was saying a little bit earlier about these calculations become a little trickier if this hasn't been scaled to 1. If this, for example, was 7, then you'd have to subtract 1/7 or 3/7 of the row, right? So it's easier just to do the scaling to 1, and then the calculation proceeds reasonably smoothly. All right. So the first row stays unchanged. So this is 1, 4, 1, 2, 1, 4. Then the next row, so the first entry is 1, 1 minus 1 is 0. 3 minus 4 is minus 1. 1 minus 1 is 0. 1 minus 2 minus 1. And 1 minus 1 is 0. And 1 minus 4 is minus 3. Okay. So we've done row 2 is replaced with row 2 minus row 1. And now row 3 we replace with row 3 minus 3 row 1. So we'll take 3 minus 3 times by 1 is 0. 6 minus 3 times by 4, so 6 minus 12, negative 6. 3 minus 3 times by 1 is 0. 4 minus 3 times by 2, so that's 4 minus 6 minus 2. 5 minus 3 times by 1 is 2. And then 2 minus 3 times by 4, 2 minus 12 is negative 10. Right. Is everyone happy with this step over here? Okay. So this was step 3. Step 4. Basically, step 4, we're just going to repeat this process. And now when we repeat the process, yes? 5 minus? No, but it should be 5 minus 3 is 2. I don't know, where do you see 5 minus 6? I mean, maybe I've made a mistake, but I can't see what you're pointing out. No, all right, okay. So, yes?
Is it wrong if maybe I can say row 1 minus row 2 to operate the negative?
Row 1 no, don't do that. Don't do that. I mean, yeah, look, technically it will work, right? But it's much easier when you're doing Gauss reduction to just have this very simple algorithm that you can follow without even needing to think, right? And then you don't have to worry about what you do. You just follow the algorithm. And the point is, and maybe this is a little bit of meta-knowledge, when I set Gauss reduction problems in the test, I'm going to assume that you follow exactly this algorithm, right? Which means that I'm going to set it up in some way that if you follow exactly this algorithm, the calculation works out relatively neatly. The marking schedule is going to have this exact algorithm used to determine the various steps. And if you present a solution which looks exactly like the solution in the marking schedule because you followed the algorithm precisely, then it's very easy for us to look and say, oh, this full marks, let's go, right? As soon as you start doing something which is a little bit, you depart from the algorithm. You do something which may work but may not. You start annoying your marker because then he has to start thinking. Right? And then I've got to look at this and be like, oh, okay, right, he's done something different. Now I've got to follow your Gauss reduction and check that you've done all the, where did you make your mistake? You don't want an annoyed marker, right? So just follow the algorithm, do it exactly like I'm telling you to do it here, and everything will work out fine. Yes? Sorry, I didn't hear that. Okay, we'll get there. We'll get there, right? We're going to run into something interesting is going to happen because of the fact that this is not square, and we'll talk about that at the end. Okay. So step 4, what we do now is we proceed. We proceed from step 2 again, but now we simply ignore the first row, right? We say the first row is fixed. Now proceed from step 2, but just look at a sort of submatrix formed by ignoring the first row. So we say, step 4, repeat from step 2. We're going to repeat from step 2, but we ignore the top row, right? Let me just grab this over here. So I'm going to put that over there. We repeat from step 2, but we ignore the top row. So what I mean by that is, okay, we just pretend that that row isn't there, right? And now we think about what do we need to do. We look for leftmost non-zero entry. It must be at the top of the matrix, and we've got to scale that so that it's equal to 1. Okay, right. So we're going to scale it so it's equal to 1. So we just take row 2 is minus row 2. Okay? So the first row, that's 1, 4, 1, 2, 1, 4. The next row is 0, 1, 0, 1, 0, 3. And the last row is 0, negative 6, 0, negative 2, 2, negative 10. We've got that. Okay, so we've got a pivot now. The pivot is this entry over here. And now we try to make all the entries underneath the pivot 0 by adding or subtracting appropriate multiples of our pivot row. So in this case, we'll have to add 6 times row 2 to row 3. So we're going to say we'll have row 3 is going to be row 3 plus 6 times by row 2. So the top row, 1, 4, 1, 2, 1, 4. Doesn't change. Second row, 0, 1, 0, 1, 0, 3. Doesn't change either. Third row, okay, here's the third row. This is going to change. So 0, then negative 6 plus 6 times by 1. Okay, that's exactly 0. Okay, and this is still 0. Then negative 2 plus 6 times by 1. So negative 2 plus 6 is 4. And then 2 plus 6 times by, okay, that's nice, 0 over there. And then negative 10 plus 6 times by 3. 6 times by 3 is 18. 18 and negative 10 is 8. All right. And now we repeat again, except now we ignore the top 2 rows. So we look at this over here, and we've got to choose the leftmost non-zero element. That's going to be this 4 over here. It's already at the top, so that's good, but we should scale this by 4. Or not by 4, by 1/4. So we scale this, we say row 3 goes to 1/4 row 3. 1, 4, 1, 2, 1, 4. 0, 1, 0, 1, 0, 3. 0, 0, 0, 1, 1/2, 2. Okay. Yes?
In that side of it, why we are not making that third row zeros, like 1 above 4 above that one?
Okay, right. So Gauss reduction happens in 2 parts. In the first part, you move left to right, making entries underneath the pivots to 0. And now we're going to move right to left, making entries above the pivots to 0. So we will still do this. Okay. Right. Yes?
So just based on how why can you not do them simultaneously? Why can you not do the top row?
It's sometimes not necessary to do the top row. It depends on what your why you're doing the Gauss reduction, right? If you're actually trying to solve the system of equations, you want to get a solution, then yes, I mean, you'll either do both at the same time or you'll go left to right and then back right to left. If all you're trying to decide is whether or not the system has an infinite number of solutions or one solution or no solution, then you don't need to do the Gauss reduction clearing above the pivots. You only need to clear below the pivots. So this way allows you to do sort of half the work if you only need half the work, and all the work if you need to do all the work, right? So, yeah, I mean, it'll depend on why you're doing the Gauss reduction. Okay, so this is now in row echelon form. So we're in row echelon form. Row echelon form means that each pivot is to the left of the pivots beneath it. Okay. And in row echelon form, we can now decide, we can see qualitatively, we can make some qualitative decisions about or qualitative judgments about the solutions. you can look at this and you can see that there are an infinite number of solutions and it's a two-dimensional subspace. And I'll explain how we see that in a moment. But after this, we're going to do the second part of the Gauss reduction, and then we can actually write down the solution, right? So at this stage, we make qualitative judgments about our problem. In this case, the system is consistent. And the null space of A has dimension 2. I'm a little bit naughty here in the sense that we haven't actually spoken about what it means for a subspace to have a dimension. But I guess we'll cover this in the next couple of lectures, right? And the way you make these qualitative judgments, very simply, is you basically just look at the shape of that. Over here we've got 5 columns. Only 3 of the columns have pivots in them. Right, the first column, the second column, and the fourth column. The third and fifth columns don't have pivots in them. So the third and the fifth columns, you have to let, I guess it would be x3 and x5, you let those be some free variables. So x3 is equal to alpha, x5 is equal to beta, or maybe x3 is equal to s, x5 is equal to t, whatever free variables you're used to working with. And that means that your solution is going to have sort of 2 degrees of freedom in it. And so your null space will be a 2-dimensional space, right? But let's actually just keep going with the Gauss reduction. We can get to the exact solution. So this first part of Gauss reduction, I said we moved left to right, making entries under the pivots 0. Now we can move back in the other direction, making entries above the pivots 0. Okay. The first part of this process moved left to right, making entries under the pivot 0, under under the pivots, above the pivots, above the pivots 0. Okay. So I guess we are now up to step, what is the last step that I wrote down? Step 4, okay. So now we're on to step 5. So now we choose the pivot in the bottom row and add or subtract multiples of that pivot row to the rows above it, making the entries above the pivot 0. So, oh dear. Hold on, give me a moment. This. Okay, so step 5, we'll add or subtract. Oh, in fact, maybe before we get to that, So now we're going to work from the bottom pivots instead of the top pivots. You work from the bottom pivots, add or subtract. Multiple of the pivot row. We add or subtract multiples of the pivot row to the rows above, making the entries above the pivot 0. Okay, so where was this last? Okay, so the bottom pivot, the bottom now leftmost non-zero entry is going to be this one over here. So we're just going to make this entry here and that entry, that's 2, equal to 0 by adding multiples of row 3 to row 2 and to row 1. So we'll take row 2. It'll be row 2 minus row 3. That will work. And row 1 will be row 1 minus 2 row 3. So the nice thing about doing this is that many of the entries don't change now. The entries to the left of your pivot don't change. You don't have to worry about them. Over here, we do have to do a little bit of thinking. So 2 minus 2 times by 1 is 0. 1 minus 2 times by a half. 2 times by a half is 1. So 1 minus 1 is 0. And 4 minus 2 times by 2 is 0. Okay, and then the second row is just the second row minus the third row. So again, these entries can't change. 1 minus 1 is 0. 0 minus a half is minus a half. And 3 minus 2 is 1. And then this last row is 0, 0, 0, 1, 1 half, 2. Yes?
If you're editing row 2, do you have to say row 2 minus something or row 2 plus something? Can you not say row 3 minus row 2?
I mean, so you would say we would replace row 2 with row 3 minus row 2.
Right, well, not specifically for this case, but just in general.
You can do that. I prefer to always think about keeping whatever row you're in fixed and changing that row in some way, because it's just, for me, a little bit more conceptually clear what I'm doing at each stage then. And then we have the next pivot element over here. So now we just have to clear the 4 above it. So we'll say row 1, we replace with row 1 minus 4 row 2. Okay. So 1, so that goes to 0. That stays there. So 2 minus 4 times by 1 is minus 2. Oh wait, no, what am I doing? I'm looking at the wrong row. Yeah, okay, we're looking at that row. Okay, so that 4, okay, so what is a negative a half times by negative 4 is 2. No, I've missed this one. Okay, and then negative 4 times by 1 is negative 4. Okay, and then the second row stays the same, 0, 1, 0, 0, negative 1 half, 1, 0, 0, 0, 1, 1 half, 2. Okay, so I realize we're just about to run out of time, but this is now what we call reduced row echelon form. And from here, it's pretty easy for us to read off the solution. So this is so we're now on to step 6. step 6, we can write down the solution. One thing which we have to do is we have to look for rows with no pivots, columns with no pivots. So those are columns with no pivots. The pivots are here, right? The columns with no pivots, you've got to introduce free variables. So write down the solution. So introduce free variables in columns with no pivots. So in this particular case, we're going to have to write down, this will be x3 is equal to, I'm going to call it alpha, and x5 I'm going to call beta. And now we can write down our solution. So we write down our solution. When we're writing down our solution, we always write it down in vector form. So we write down x1, x2, x3, x4, x5. That's a vector. And the shape of this solution, or the form of this solution, is always going to be some constant vector, which may just be the constant vector 0, 0, 0, 0, 0. It'll be that constant vector 0, 0, 0, 0, 0 if we've got a homogeneous system. In this case, it's not homogeneous, so we'll have some actual non-zero entries there. And then for each free variable, there'll be another vector. Each extra vector here corresponds to a free variable. And now we just sort of read off each row. So that first row says x1 plus alpha plus 2 beta is equal to minus 4. So x1 is equal to minus 4 minus alpha minus 2 beta. Then the next row says x2 minus a half beta is equal to 1. So x2 is equal to 1, no alphas, and that minus a half beta goes across to the other side, and you get a half over there. Then the next row, x3 was free. Oh, we said x3 was just equal to alpha. So x3 is just equal to alpha. x4. So x4, if we look at the third row of the matrix, says x4 plus a half beta is equal to 2. So x4 must be equal to 2 minus a half beta. And then the last one, x5 is equal to beta. So x5 is 0 constants, 0 alphas, and a beta. And we're now done. All right. So I'm sorry that I've gone a couple of minutes over time. I'm going to hang around now if you've got questions. Otherwise, I'll see you tomorrow.